Restart. Sorry? Yeah, just give me a minute here. Okay. Hear the audio. All right. Can you guys hear me? Okay, great. Welcome to the fourth tutorial in SIGMOD. This tutorial is about differential privacy in the wild, a tutorial on current practices and open challenges. Okay, so this tutorial is going to be presented by three presenters. My name is Ashwin. You don't need to know my last name unless you take a course with me. There is Michael Hay, who's an assistant professor from Colgate University, and Shi He, who's a PhD candidate from Duke University. Sort of to introduce us, I sort of wrote down one sentence about what sort of keeps us awake at night. So the question that sort of keeps me awake at night is, what does privacy mean mathematically? And we'll talk a lot about how to formalize privacy for using mathematical privacy definitions. Michael has done a lot of work on differential privacy, but more about algorithm design and how do you make these privacy algorithms useful. And a lot of Shihe's work is about, can privacy algorithms actually work in real systems? Okay, all right. So let's dive in. So I'm sort of preaching to the choir. I'm at SIGMOD, so data is the currency, right? Everything about us, around us is increasingly data-driven. And all of this, much of this data that is driving the revolution around us is data that is collected from individuals, right? These data are aggregated, and they're used for a variety of interesting purposes, right? So our information that we disseminate through, for example, web searches and so on, are used for advertising, right? The information collected from us about genome are used for genome-wide association studies that help improve, push the boundaries of what we know about medicine. And the way we travel and our mobility patterns that are collected through our cell phones can be used for mobility planning, city planning, and so on, right? Well, there are a number of positives for using aggregated data. It's a double-edged sword, because data that is personal to individuals is, well, personal, right? So there are a lot of sensitive information that can be collected through these systems. And in particular, these information can be used to create harm to individuals, right? So for instance, your race can be used for discriminating against you, right? Your sexual orientation and medical history can potentially cause physical or financial or psychological harm to you if you are discriminated against based on them, right? So to sum up, aggregated personal data is made publicly available in many forms, as de-identified medical records, as statistics that have been released by, for example, the US Census Bureau, and also by predictive models, which are used for advertising and targeted advertising. Okay? So one may think, so what's the big deal, right? This data is not about any individual. It's aggregated data. We are not releasing, say, the genome of a single individual. You're releasing some aggregate statistics about the genome, right? Why is that a problem? As long as you're sort of hidden in a large crowd of other people. The challenge here is that anonymity is not enough. And there have been a string of very high-profile privacy breaches that speak to that. So one of the most famous ones happened in 2006 when AOL, how many of you heard of AOL? Yeah, quite a few of us, right? They used to run a search engine, maybe they still do, and they decided, and they actually did, for good intentions, to take a large fraction of their search logs collected over a significant period of time and release them for research, right? So of course, they can't release the entire, all the information because they have sensitive information about identities of people. So they said, okay, we'll take the user IDs of people and remove them and replace them with random numbers, right? But still, they did release whether the two searches were made by the same person or not. Just looking at the searches, reporters from New York Times were able to uniquely identify a single individual, actually figure out what her name was, where she lived, what her age was, that she had pets, that she had certain medical conditions. I would actually go knock on her door and ask her, did you make these searches, right? So anonymity is not enough because every bit of information is actually very highly identifying of individuals, right? And not only this aggregated data or de-identified data is problematic, even releasing predictive models can breach your privacy, right? There was a very interesting paper a few years ago which showed that based on a linear regression model that is trained on some training data set, an attacker with some information about a few of the individuals in the training data set could actually learn sensitive information about individuals in the training data set and the fact whether they were in the training data set or not, right? So therefore, as these attack algorithms and these privacy breaches become more and more sophisticated, what we need are some sort of principled ways to analyze whether an algorithm is, which may purportedly be only releasing sort of aggregate statistics, whether or not it actually leaks information about individuals, right? And you need some way to analyze algorithms so that you get provable guarantees of privacy, right? And that is the goal of differential privacy and all of the other sort of formal privacy definitions that we will talk about today, okay? So again, please stop us whenever you have questions. The outline of this tutorial is going to be the following. So we're going to start with asking the question, what does privacy mean? And sort of talk about what privacy is and what privacy is not, okay, and what we think of privacy as. Then we'll give an introduction to differential privacy, and we'll talk about sort of the how do you answer queries on tabular data under differential privacy. That's the first part of the tutorial, and then there'll be a break. Then we'll come back after half an hour. And in the second part, we'll talk about how do you use differential privacy to build machine learning algorithms. We'll talk a little bit about privacy in the real world, and also sort of another set of applications on social networks and trajectory data. So to go a little bit into detail about each module, the first module will actually try to formally define the privacy problem statement. We'll talk about what privacy is not in this talk, and privacy can mean many different things. And we also talk about what privacy is. Okay. In the second module, we'll define differential privacy. We'll describe some of the basic algorithms, the Laplace mechanism and the exponential mechanism. We'll actually go through some of the proofs of why these satisfy differential privacy, and we'll talk a little bit about how much error they introduce when they're used. And we'll also talk about the basic composition theorems. In module 3, we'll talk about how do you answer queries on a database. How do you answer counting queries? How do you answer other sort of linear queries? We'll talk a little bit of theory, but mostly about sort of a survey of ideas and how do you design algorithms. Okay? We'll start the second half of the tutorial with some recent work on machine learning. And then we'll talk about privacy in the real world. I'll talk to you about a couple of real-world deployments of differential privacy and the challenges that are faced in deploying differential privacy and the privacy beyond sort of just thinking about it as tabular data. And finally, we'll look at two applications of differential privacy to non-tabular data, which is like graphs and social networks, and sort of continuously streaming data in non-tabular data. Okay? All right. So what do we not cover in this tutorial? So it's going to be about differential privacy, but what we do not cover is sort of things like securing data using encryption, like guarding against attacks that come in and sort of steal your data, right? That's not what we're going to cover. We're not going to cover computational encrypted data. We're not going to cover things like computationally bounded differential privacy, if you've heard of that. We're not going to talk about anonymization schemes or de-anonymization, and we're not going to talk about access control either. Okay? All right? So with that, we can start the tutorial. Any questions at this point of time? All right, sounds good. So let's start with the problem formulation. All right. So we envision a system where the following happens. You have a bunch of individuals, and each individual, for now, let's assume they have a single record that describes all the data about them. Okay? Then there are a bunch of data collectors, and these data collectors are collecting information from these different individuals. Okay, so the data collectors could be, for instance, a hospital that is collecting patient data, Census Bureau is collecting demographic information, or Google that's collecting your web search history. Okay, and then each of these data collectors don't just collect this data. They want to release some aggregate information out, either in the form of sort of de-anonymized data sets so that epidemiologists can do some research, or in the form of statistics so that economics can work on it, or in the form of sort of predictive models. Okay, so there's some function that they apply to this database, and they release that. Right? Okay. So before I sort of formally define what the problem itself, let me start with an example of a privacy breach. Okay. So there's a very famous privacy breach called the Massachusetts Governor Privacy Breach, and what happened here was there was a data set that was released by a group insurance company, which basically served all employees of the state of Massachusetts. Okay, so this had information about their diagnosis, their visit date, their procedure, and so on. But of course, they can't release all this information as is, so they removed the name and social security number. Okay. Now, a researcher got hold of this data set and found that she could join this data set with the voter registration list of Massachusetts, which basically contains all people who vote in Massachusetts, right? And she found that she could join these two tables based on the attributes zip code, birth date, and gender. All right? So she found that there were some records that were uniquely identified by this combination of zip code, birth date, and sex, and one of them was the governor of Massachusetts. So there was exactly one record on the left-hand side and one record on the right-hand side, and so therefore you could link the name of the governor to the diagnosis, and that is a breach of privacy, right? So it was not only the governor of Massachusetts who could be uniquely identified. Turns out that 87% of the US population could be uniquely identified using the 9-digit zip code, the full birth date, and the gender, right? And even though this looks like a innocuous combination of attributes, it's sort of almost an identifier. So it's called a quasi-identifier, right? And so since 87% of the US population can be revealed, this is not a good idea, right? So this kind of an attack is called a linkage attack, right? So the goal of the statistical database privacy problem is the following, right? So you have a server that is collecting all of this information. In the previous case, it was this insurance company. And let's assume that the server itself is trusted. And the server is releasing some information out. It's trying to compute some function in this database. So in the previous case, the function was just release all the records after dropping the name and social security number, right? And that function is provided by the analyst, because that analyst is interested in this data without the name and social security number, right? But the problem is this output can disclose sensitive information about the individuals, which, as we saw, you could do this linking attack where you could take this output, link it with some other database, and you could reveal individual records from the original database, right? So the goal of the statistical database problem is to replace this function with a different private function that takes as input this database and some sort of privacy parameter, epsilon. Okay? So the goal of this new function is to ensure privacy for individuals controlled by this parameter epsilon, and we'll formalize all of this more clearly later, right? So you want privacy for individuals in this data set, okay? But the goal of the function itself is to approximate the original function, which is an aggregate over this database, okay? So you want to, as part of the utility constraint, you want aggregate information about this data to be revealed almost exactly, or with low approximation error, but at the same time, you want privacy of individual records in the dataset. Okay? Right? Another version of this problem is one where the server is not trusted. And I'll show you examples of where this occurs. And now if the server wants to compute this function, the people don't trust the server. They only trust themselves, right? And the goal there is to basically, you want the individuals, you want to create a mechanism where the individuals can perturb their individual records and send the perturbed records off to the server such that privacy is guaranteed for each of the individual. You can't reconstruct the individual records from the perturbed answers. But you can't just encrypt the values, because what you want to do is you want to be able to reconstruct the answer to the original function that the analyst wants to compute, okay, with low approximation error. All right. So why are we interested in this problem? Turns out this is a universal problem, and we see this all over the place, right? So in the case where you're assuming that the server is trusted, you can come up with many examples where this actually happens in real life, right? So for instance, the application could be a medical application where the data collector is a hospital. The private information is, for example, the disease of an individual. You don't want to disclose the disease of each individual record. The analyst is like an epidemiologist, and the function is just the correlation between, say, disease and geography. And you don't need to reveal each individual disease to compute this correlation, right? It's only an aggregate property of the data set. There are other settings where the data collector may not be trusted, or the data collector may not want to collect all the records and store it on their database just for liability reasons. And I will actually talk about that later. One example of each of these when we talk about real applications in the second half of the tutorial, right? So for instance, one example is the data collector may be Verizon and AT&T. You either may not trust them to preserve your privacy, or the data collector themselves may not want to just hold on to the data, right? And the private information may be the location of individuals, and the function you want to do is sort of traffic prediction, right? You want to use these locations of individuals to do traffic prediction. Okay? All right, any questions at this time? Sounds good. All right, so now let's talk about, so we've defined this statistical database privacy problem, okay? So first, let's talk about what it is not, right? And the first thing you might think of is, why can't I just use encryption, right? So statistical data privacy is not encryption, because in encryption, what you're trying to do is you have two parties, Alice and Bob. Alice wants to send the message to Bob in such a way that no sort of man in the middle, Charlie, can actually read this message, right? So what Alice can do is Alice can take the message, encrypt it, put it in a box, lock it, and send the box over to Bob, and Bob, who also has the key, can unlock it, right? In statistical database privacy, Bob is also the attacker. So Alice wants to send the information to Bob, the aggregate information to Bob, right? But Bob should learn the aggregate statistics, but not learn sort of the individual level properties of the data, right? So it's a very different problem in that sense. So another problem that is very well studied in the database community is computation on encrypted data. You take your data, you basically encrypt each of the individual records, and you want to compute, for example, a function on these encrypted records. And there's a lot of work on fully homomorphic encryption that tries to solve this problem. This also does not solve the statistical database problem, right? Because the statistical database problem, the Bob is actually allowed to learn these aggregate statistics over the data set, right? In the computation over the encrypted data problem, Alice stores all the encrypted data on a server, and the server can compute on this encrypted data, but does not allow to know the answer to any of these functions. Only Alice is not allowed to know the answers to these functions. Right? Statistical database problem is also not the millionaires problem. How many of you heard of the millionaires problem? Right? So the millionaires problem is basically you have a bunch of millionaires who are sitting around. They want to find out who has the most money, but they don't want to tell each other how much money they make, right? So this is also a special case of a general problem called secure multi-party computation, where you have multiple different parties, all of which want to collaboratively compute a function in such a way that each individual party only learns their input and the output to the function, okay, and no other information. However, in statistical database privacy, even the function output should not be learned exactly, because the function output, as we saw before, could leak information about individual records in the dataset. Okay? And finally, statistical database privacy is not access control. It's not a simple case of I will allow Bob to see the record, I will not allow Charlie to see the record, right? It's more complex because you want to allow Bob to learn sort of aggregate statistics, but not learn sort of individual specific statistics. Okay? And usually access control is a setting where you have multiple parties, multiple agents who are sharing multiple pieces of data. Here you just have a single person single data collector who's collecting all the information about individuals, and a single person analyst who's trying to analyze this function. Okay? So when you solve real world problems, right? Real world privacy problems, you're building like a enterprise system, you need all of these, right? You need encryption when you're communicating data across. You need secure computation if you have multiple, if you're storing data in multiple places, and each of them should not be revealing information about to the others. You need computational encrypted data when you want to use an unsecured server. So what differential privacy and statistical data privacy allows you to do is actually allows you to mathematically quantify how much information is leaked in each of these use case scenarios, and is in some sense orthogonal to all of these solutions. Okay? All right. So now that you talked about problem formulation and basically what privacy is not, so I still haven't formally defined what privacy means, right? So let's talk a little bit about that, and let me set up a few desiderata before we go into a formal definition for privacy, right? So one way you can sort of informally define a privacy breach is the following, which is a privacy mechanism M causes a privacy breach if it allows some unauthorized party, this attacker guy here, to learn some sensitive information about any individual in the dataset D. Right? That could be one way to define a privacy breach. Right? But that's not enough, right? Because maybe the attacker could already learn the sensitive information even if he did not have access to his dataset D. Right? The fact that every individual who goes to a hospital is a human. Yeah, they know that even without access to this database, right? So therefore, first way you can talk about privacy breaches is basically that you're learning new information, right? Privacy breach happens if the unauthorized party is allowed to learn some sensitive information about an individual, which the attacker could not have learned without access to this mechanism, right? That makes sense as a definition of privacy breaches. So now let's look at this question. So let's say there is Alice, okay? Alice is your neighbor, you know Alice smokes, right? And then there is a study that is released. It's a very a study that is a study that was published in, say, Nature, which basically says that smoking causes cancer, and it definitively proves that, right? Now, if I have access to these two facts, right, I can now, with high probability, say that Alice has cancer, right? So then, do we say that releasing this study causes a privacy breach? Right? I mean, Alice may not even have been part of the study. Right? It could be a study of participants that are completely unrelated with Alice. But it's still sort of, you're able to learn something new about Alice. So when we talk about statistical database privacy, we say that this is not a privacy breach. Okay? Because irrespective of whether Alice was involved in the computation or not, her privacy is being breached. In some sense, what is happening here is you're learning some law of nature, right? The fact that smoking is correlated with cancer. You're not learning anything about an individual, right? So therefore, another take at a revised definition for privacy breaches could be that a privacy breach is a privacy mechanism that allows an unauthorized party to learn sensitive information about an individual Alice in this database, which the attacker could not have learned without access to the mechanism on an input where if Alice is not in the dataset, right? So you can already start seeing that defining privacy is not sort of trivial. It's fairly subtle, right? And that's why there's been a lot of research on defining privacy, and we'll talk about some of that during this tutorial. Okay, so before I go into the next sort of desiderata, I want to give you another example. So remember the linking attacks we had, where we could link two databases, and if there was a unique record in the join, then you could basically find, say, link name to diagnosis, right? One way to avoid that is using a technique called k-anonymity. It basically avoids linkage attacks. Basically, all you make sure is that when you release a data set, every record looks like k other records. So you never have a single record when you join with any set of attributes. Okay? That sort of makes sense. So it avoids the linking attacks. Is that a good way to define? Is that a good way to achieve privacy? Turns out no. I mean, so this is an example of k-anonymity. I have a bunch of records. So maybe zip code, age, and nationality are the quasi-identifiers. I can coarsen all the records so that now, based on those three attributes, every record looks like K3, in this case, 3 other records. Right? So the problem is that attackers can have background knowledge. Right? They may know something about the individuals in the table already. So for instance, the adversary may know that there's an individual Umeko in this table, and the fact that Umeko has this zip code, this age, and this nationality, so she's amongst the first 3 records. And she may also know that Japanese have very low incidence of heart disease, and therefore they know that Umeko has cancer. Right? This is fairly straightforward, right? So attackers, for example, you may know some background knowledge about your neighbor, right? And you know the neighbor is in this patient database, and that can allow you to learn more information beyond what is released by this hospital, right? So therefore, another important desiderata for privacy definitions is that a privacy mechanism must be able to protect an individual's privacy from an attacker who may possess some prior knowledge about these individuals in this data set. So despite their prior knowledge, and even if you don't know what the prior knowledge is, you should be able to give some guarantees of privacy. Okay? Here's a last example before I sort of finish these desiderata. In this example, we're going to talk about a system which is called HCUPNet. It allows you to dynamically look at sort of tabular summaries that are released by hospitals about number of patients of a certain type, number of patients discharged in a certain time, and so on. Okay? Now, it's very sensitive information because, for example, you can tabulate things like the number of hospital discharges in New Jersey of ovarian cancer patients in 2009. Right? So here it is tabulated by age and race, and clearly there may be some age-race combination. There's only one individual or no individuals, right? So wisely, these guys, what they've done is, if the number of patients of a certain type is small, they've sort of suppressed those values. So in particular, whenever the count is less than 10 in this case, they suppressed it, so they get sort of k anonymity with k equal to 10, for example. Right? But what's wrong with this? So it turns out, if you actually look at these numbers closely, right, this cell is actually the number of the column sum for this column. And this cell is the row sum for this row, right? So you basically have an equation that you can solve exactly. So even though they try to hide the fact there's only one individual here, you can just reconstruct it based on the other values, right? And what's more, you can actually write this as a system of equations, and you can actually get tight bounds on every other cell, right? So you can get tight bounds on all of those cells based on the fact that the total, so row total is 3, and this is 1. So these are all have to be within 0 and 2. You can iteratively improve this using a linear programming solver, and basically you can get tight bounds everywhere, right? In addition, you can actually connect this with other data sets, and you can make very strong deductions about individuals in the data set. So in fact, you can say that when linked with, in this paper that talked about this attack, they showed that when linked with queries from other statistics, they could figure out a lot of information about a specific individual. And once you have so much information, you can actually identify them, right? So the problem here is this problem of multiple release, right? It's not necessarily true that you only release things once, right? So even when you have multiple releases, you should be able to guarantee some amount of privacy. So in k-anonymity, for instance, even 2 releases are enough to sort of uniquely identify individuals, and that's a problem. So an important desiderata, again, is that a privacy mechanism must satisfy composition. which is you should allow for a graceful degradation of privacy with multiple invocations on the same data. Okay? And a final desiderata, and this also means that if you take your data set and you release something, and that satisfies some privacy condition, just running another algorithm without looking at the data set anymore, or what we call post-processing, should not further degrade the privacy guarantee anymore. Okay? And the last desiderata is that privacy must not be achieved through obscurity. You should not say that I'm private because I keep the algorithm secret. Right? You should be able to release the algorithm and still ensure privacy. Okay? So with this sort of desiderata, I'm going to sum up now. I would say that so statistical database privacy is the problem of releasing aggregates while not disclosing individual records. And the problem is distinct from a lot of things that have been very well studied, like encryption, secure computation, and access control, and so on. And defining privacy is not going to be trivial. It's actually very non-trivial. And we'll talk about differential privacy and other privacy definitions in the rest of the tutorial. Okay? So any questions at this point of time? Yes? Go ahead.
Is there any formal definition of what background knowledge is?
Do you have a question?
Not knowing sensitive identity is probably the most strictest definition. Is there any other definition?
So the question is there any formal definition for what an adversary's background knowledge is? So we will actually talk about that in the second half of the talk, what a formal definition for background knowledge is. Okay? Yeah.
Hi, just a very general question. You mentioned the example of Alice and smoking statistics, right? And this is quite intuitive on why this is not a privacy breach. But can you give a similar example where it is a privacy breach? I mean, according to
so for instance, if Alice is actually in the data set, right? And let's say Alice was some sort of a unique kind of a person. Let's say Alice was the only person who had red hair, right? And then based on the study, you release that there was only one individual who had red hair, and that red hair has cancer. That red-haired person has cancer, right? Then if you knew this was the release and there was only one individual in the entire universe who had red hair, then you knew Alice is in the data set and Alice smokes. Okay?
But that statistic is not very similar to the aggregate statistic.
So the problem is that so the question is that is not very similar to an aggregate statistic, right? A lot of times when people release aggregate statistics, right, you aggregate it, but also you group by some group by keys, right? So you say aggregates based on location. Turns out that some locations may be very sparse, right? Whereas some locations have a lot of individuals, right? Also, when you're releasing multiple different aggregates, right, it's easy to see how the combinations of those can lead you into sparse areas. Okay?
So this is definitely a breach if you can 100% uniquely identify the individual.
So the question is, I didn't understand that question. Could you repeat that?
You get an example where Alex is the only one with red hair. It did say that the person with red hair is like having this chance of getting cancer. But if the database say that there's 100 of them, and so the probability is just 1 over 1.
Right.
And it is still considered as a privacy breach, even though it's not 100% that you can identify Alice on that.
So in your specific example that you're talking about, maybe it's not a privacy breach, but if you keep releasing multiple such statistics, it could potentially lead to a privacy breach. So let's talk about some of these formal privacy definitions, and maybe we can come back to your questions. Okay? Okay, so now I'm going to hand it over to my colleague, Michael, who will start talking about differential privacy. One other question, okay? Can you use the mic, please?
So again, what's the?
Can you turn on the mic, please? Yeah.
Again, so what is the definition of breach? Like, I can infer like one.
So I have not formally defined what a privacy breach is yet.
I see. Okay.
I've sort of given you a flavor for what it can or cannot be, and some desiderata for it. So we'll talk about formal definitions that will formalize what a privacy breach is. Okay? All right, so now Michael will talk about differential privacy.
Can you hear me okay? Does it need to be higher? Is that better? Okay. Okay, thank you, Ashwin. Yeah, so these are great questions, and we can get into sort of formal privacy definitions now. So in this next module, I'll define differential privacy and talk about how it satisfies some of the desiderata that Ashwin just introduced. Okay, so I'll walk through the definition of differential privacy. We'll look at some basic algorithms for differential privacy. So if you're new to this, these are useful algorithms to know about. They're used all the time in the literature, and we'll talk about some of the composition theorems at the end. Okay, so differential privacy is a property of the algorithm that you're going to run on the data. Okay, so I'll show you the formal definition in a second, but then I'll sort of unpack the definition piece by piece. Okay. Okay, so we imagine that we have an algorithm that's going to run on some data set. So D1 here is a data set of tuples. The color indicates sort of the type of the tuple, I guess. And the algorithm produces some output. And I actually don't care that much about what the particular output is. It looks like in this picture that we're producing some kind of like other sort of data set. Maybe the tuples are sort of slightly different shaped and different colored, but I'm just producing some output with this algorithm. Okay. And what the definition of differential privacy requires is that for every pair of inputs that differ by one row, so one record in the database, so D1 and D2, and for every possible output that you could produce, if the algorithm satisfies differential privacy, then the following ratio holds, right? So the probability of producing that particular output when the input is D1 over the probability of producing that same output when the input is D2, right? The probability that ratio has to be bounded, and it has to be bounded by e to the epsilon, okay? And so the intuition behind this is that the adversary should not be able to use the output O to distinguish whether the input was D or D1, okay? But let's unpack this definition a little bit. Okay, so first of all, why are we looking at pairs of data sets that differ in one row? So the idea here is that we're simulating the presence or absence of a single record, which may correspond to one person's, private data. We'll actually come back to that in the second half of the tutorial and revisit that notion, okay? Why are we looking at all pairs of data sets? Okay, well, what we want is a worst case privacy guarantee notion. And so here, one way to think about it is, suppose that our database is describing the salaries of individuals, and we have a bunch of sort of folks who are, middle class, and then the additional record there is Bill Gates, right? So he's clearly an outlier, and we'd like this guarantee to hold even if that one additional record we add is a statistical outlier from all the other records in the data set. Okay. And then why all outputs? Okay. So we can imagine the set of possible outputs that an algorithm could produce. And differential privacy says consider the probability of producing each of these outputs. So I guess one thing I didn't say before is this algorithm is going to be a randomized algorithm. So the output that it produces is essentially generated by flipping some coins, and you output a particular output with some probability. So we can think of the set of all possible outputs, and then think about the probability that we would have generated that output given that the input was D1. And suppose the distribution looks something like this, so that red output is more likely when the input is D1. We could consider the probability distribution when the input is D2, okay? And so we get a different probability distribution, those green bars over on the far right. And then what we want to do is sort of compare these two probabilities for every single possible output. And we want to look for the worst possible case. So maybe it corresponds to this one here, which it sort of suggests, right? There's more red tuples in the first, in D1 than there are in D2. And so maybe it's more likely that we output this all red database, all red output when the input is D1. Right? And we want to bound the worst case probability because again, it's a worst case notion. We want privacy to be protected regardless of what output is published, okay? Okay, so so finally the privacy parameter, right? So back to the definition. So for every pair of inputs that differ in one row and for every output, we want this probability, their probabilities to be similar, okay? I just rearranged the equation a little bit there, but we want these two probabilities to be similar. They can differ by this e to the epsilon term, okay? And epsilon is a privacy parameter that we can actually specify when we invoke a differentially private algorithm. And that parameter controls the degree to which D1 and D2 can be distinguished, okay? So the smaller epsilon is, the more similar these probability distributions are to each other. And so intuitively, the more privacy you have. On the other hand, the smaller this is, basically the more noise you have to add into your computations, and so you can expect less accurate results, and so worse utility. Okay. So that was the definition of differential privacy. Now I'd like to go in and describe a few different algorithms, and we'll see how they satisfy differential privacy. These are kind of basic building block algorithms that are used in a lot of state-of-the-art differentially private techniques. Okay, so maybe first we'll start by asking a question of, could a deterministic algorithm satisfy differential privacy? So I indicated that the algorithms are randomized, but is it possible to design a deterministic one? Well, it turns out that non-trivial deterministic algorithms do not satisfy differential privacy. And so I'll show you with a small example here. So we have this kind of space of all inputs and then the space of all outputs. And what I mean by a non-trivial algorithm is that basically a trivial algorithm would just map all inputs to the same output, right? So it just always outputs 1 no matter what the input is. That satisfies differential privacy, but it's a trivial algorithm that's not interesting. So non-trivial means that you get, like, there's at least 2 possible outputs that you could experience running on different data sets. And so these, such a deterministic algorithm wouldn't satisfy differential privacy, because what you can do is, as long as there's 2 possible outputs, then you can consider the space of all possible inputs, and you can find a pair of inputs, 2 different data sets that differ by just 1 record. And on one of those data sets, you're going to output that red triangle, right, with probability 1. And on its neighboring data set, so a data set that differs by just 1 row, you're going to output that red triangle with probability 0, and deterministically, you're going to output that green triangle. Right, and so if you remember the definition of differential privacy, it says, for all possible outputs, we have to bound the ratio of these 2 probabilities, and here we have a ratio of 1/0, so it's unbounded, okay? So deterministic algorithms are out. What about random sampling? You know, there's some randomness in sampling, maybe that can provide some privacy. So it turns out that that also does not satisfy differential privacy, and to see why, so consider the following. So suppose here's our input. We're just gonna draw a random sample of records from it. And suppose we generate this output. So that red tuple ended up getting included in the output. Well, there's a neighboring data set where that red tuple is excluded, right? And if we think about the probability of producing this particular output, right, the probability of producing that output is 0 when the input is D2, right? And so therefore it implies that this ratio, right, is unbounded. So random sampling is also out. However, random sampling actually intuitively does give you some privacy, and you can use it to amplify the privacy guarantee of a differentially private algorithm. And I won't go into that, but random sampling can provide some privacy if you kind of incorporate it appropriately into your techniques. Okay, so let's look at a tried and true technique of output randomization. And the basic idea here is you have some analyst who's going to ask a query of the data. And what you can do is you can compute that query on the data and then add noise to the answer somehow, and then return a noisy answer to the analyst. Okay, and what you want to do is add enough noise so that the answer doesn't leak too much information about the database, but you also want to add as little noise as possible, right? Because you want the noisy answers to be close to the true answers. So one specific example of this kind of answer perturbation is the Laplace mechanism. So given a query, you compute the true answer, QD, on the data set. And then you add random noise, so this little eta symbol, and that random noise is sampled from the Laplace distribution. So the Laplace distribution is similar to a Gaussian distribution. It's symmetrical around 0. It has slightly longer tails than a Gaussian. And it has a scale parameter, lambda, which controls basically the variance of this distribution, okay? And so what we set lambda to is going to depend on the query that the analyst is asking, okay? So intuitively, if that query is sort of, yeah, well, we'll see exactly how we set lambda. Okay, but that's the idea, is we add random noise to the query answer. So how much noise do we need to add? what we can do is we can look at the sensitivity of the query that's being asked. Okay. So we consider some query that takes in the database and maps it to some real number. Okay. And SQ is the sensitivity of the query. And it's basically the smallest number such that if I take any two data sets, and here I say neighboring data sets, by that I mean they differ by just one record. Okay. And we look at how much the query answer can change, right, between those two. We want to consider the maximum possible change, and that's the sensitivity. Okay. So basically, intuitively, what this is saying is, if I were to add one more record to the database or remove one record from the database, how much could I change the query answer? Okay. And so you can show that if the sensitivity of the query is, say, S, okay, then if I set the scale of the Laplace noise, so lambda, to be S over epsilon, that satisfies differential privacy. Okay, and I can actually come back in a second and walk you through that proof. But let's just get a sense of what this sensitivity notion is with some examples. Okay, so what about a count query? So I want to know how many people in this data set have this disease, right? Well, the sensitivity of this is 1, right? Because if I add or remove one person from the data set, whatever the current count is, I could possibly increase it by 1 or decrease it by 1, or maybe it would stay the same if the person doesn't have the disease. Okay. So for this particular data set, we could use the Laplace mechanism by computing the correct answer, which would be 3 in this case. And then we could add random noise to it, that eta term, where eta is drawn from a Laplace distribution with scale 1 over epsilon. Okay, so that's an example of applying the Laplace mechanism to a count query. What about a sum query? So I want to know, the total salaries of all the employees in a particular company, something like that. Okay. Well, there, if we impose some restriction on the range that those values can take on, so we have a lower limit for, say, the salary of an employee and an upper limit on the salary of an employee, then the sensitivity is B, right? Because if I add one more person to the database, right, it could increase the salary by B. Okay. In terms of showing that the Laplace mechanism satisfies differential privacy, I can just walk you through a very simple proof. So let's consider two databases, D and D prime, and they're neighboring, so they differ by just a single record. And then we'll just consider some output, so any arbitrary output. And we can consider that ratio that appears in the definition of differential privacy. So the probability of seeing this output given that the input is D over the probability of seeing this output given that the input was in fact D prime. With the Laplace mechanism, right, what I'm saying is what's the probability that the true answer plus noise is equal to that output O in both the numerator and the denominator there. The only difference is the true answer might be different, right? It's QD on D and QD prime on D prime. If I just plug in the density function for the Laplace distribution, I get these terms here. Okay, and then I can use the triangle inequality, right, and consider that the distance, right, from QD to O, and then O to QD prime is at most the distance of QD to QD prime, right? And then that term right here, so the distance between these two is bounded by the sensitivity, right? That's exactly how much the answer could change given the addition or removal of one person's record. And so that's bounded by SQ. And then I set the scale of the Laplace noise to be, so lambda is exactly equal to SQ over epsilon. And so the SQ terms cancel out and I just get e to the epsilon. Okay, so that's the privacy of the Laplace mechanism. In terms of how accurate it is, right, so one nice thing about the Laplace mechanism is you can take any function you want to compute on the data, and all you have to do is figure out its sensitivity, and then you can add noise. It does expect any function that outputs a real number, I should say. And so the accuracy of it depends on the sensitivity. So lower sensitivity functions will be more accurate. And of course, it depends on epsilon, right? So remember, smaller epsilon means more privacy. And so epsilon here is in the denominator. So as it gets smaller, the variance of the noise gets larger. So smaller privacy does mean noisier answers. Or sorry, more privacy means noisier answers. Okay, so that's the Laplace mechanism. And that works great for any function that outputs a real number, but sometimes you have a function that outputs something from, say, a categorical set. So, and so for that, we can use the exponential mechanism. So for instance, suppose we wanted to compute the query, what is the most common nationality in this room, right? And we have a set of possible nationalities, okay? Well, what we can do is use the exponential mechanism. And the basic idea is the following. So we have some arbitrary function, and it can be deterministic or probabilistic. And we want to basically make a differentially private version of this function. So in order to use the exponential mechanism, what you have to do is come up with a scoring function, okay? And this is a function that basically takes an input, so a database, and a possible output, say O, and it assigns a score to it. So intuitively, this is basically how much would I like to output this output if given that the input was this input. So to kind of instantiate this with our example, we could let D, the database, be the set of the nationalities of a set of people, right? And then DO being the number of people with a particular nationality. And F of D is the most frequent nationality in the data set, okay? Then our scoring function, basically how much would we like to output this particular nationality, right, would be the count of the number of people with that nationality in the data set, and take the difference between that and the count of the most frequent nationality in the data set. So basically this will prefer outputting the most frequent nationality, but you may output, say, the second most frequent or the third most frequent, and those will get lower scores. Okay. So what do we do with this scoring function? Well, first we have to talk about the sensitivity of the scoring function. So intuitively, it's the same idea as the sensitivity of the Laplace mechanism. Just mechanically, it's slightly different. So when we think about sensitivity, we're thinking about all neighboring data sets, so D and D prime. But the scoring function also takes in the output O. So we consider how much adding or removing one particular person could affect the answer. And then we take the max over all possible outputs that you could produce. Okay. So that's the sensitivity for the exponential mechanism. And then to actually produce an answer, we take that scoring function and we sample a probability from this distribution. Okay. So basically the probability that we sample a particular output is proportional to the score exponentiated. Okay. So the denominator here is just a normalizing term that sums over all the possible outputs that we can produce. Okay. Another key building block is randomized response. Okay, and we'll see a concrete example of randomized response in the second half of the tutorial, and it was used inside a real-world deployment of differential privacy. So the basic idea of randomized response is rather than sort of collecting all the data and then letting people issue queries over it and returning noisy answers, here we're going to actually perturb the data itself. Okay, so here I'm just going to illustrate it with this very simple data set where basically it's a collection of records just containing a single bit, right? Yes or no, does the person have this disease or not? And the basic idea behind randomized response is that with probability P, we'll report the true value, and with probability 1 minus P, we'll flip the value, okay? This is actually a very old technique. This was invented in the 60s by sociologists who were trying to interview people and ask them very sensitive questions, maybe about their political orientation, sexual orientation, illicit activities that they may be involved in. Right? And the idea here was that you could ask them a question and they could sort of flip a coin and then potentially tell you the truth if the coin comes up one way and lie if it comes up another way. Okay, so this satisfies differential privacy. And one way to think about it is if you think about this collection of records, if I wanted to change one of those records from, say, yes to no, okay, and then I want to know what's the probability of a particular output, so a particular configuration of yes-no answers. Well, if I consider the probability of that output given the original database, and then I consider the probability of that output given the database where I modify one person's answer, so that's what D prime is. Well, this ratio here is either P over 1 minus P or 1 minus P over P, depending on, or the max of those two, right? And so this satisfies differential privacy if and only if P, the probability, falls between these two values here, right? So there's a relationship between P, the probability of keeping the answer, and epsilon. Okay. So one thing with randomized response is so I could apply randomized response, and I could flip everybody's value from using this procedure. And then in the end, I get this sort of new database of yes, no answers, right? But some of them have been corrupted by this flipping process. So now what I want to do is I want to say, well, how many people, I want to come up with an estimate for how many people really have the disease, right? What I can observe is how many yeses there are in this perturbed data. So suppose N1 is, N1 out of N of the people replied yes, and the rest said no, okay? So this is what I can see in the randomized output. So how do I estimate pi, right, the fraction of people that actually have the disease in the original data, right? I don't have access to the original data, just this perturbed data. So I can actually come up with an estimate for pi by doing some post-processing of the data that I get out, okay? And so basically this is a small example of statistical inference. And what you do is you take N1 over N, so that's the fraction of people that have yes in the perturbed data. And you can basically make some adjustments to it, subtracting off 1 minus p and then rescaling everything by 2p minus 1. In expectation, this estimate here is exactly equal to the true proportion in the input. And then we can look at the variance, so how accurate this estimate is. And it turns out that you can decompose the variance into two components. So one component is just based on sampling. So if you think of the original database as a random sample from the population, you're going to have some random variance just from the fact that you took a sample. So that's what this term is. And the second term is the variance due to the coin flips. Okay. Okay. Let's see. Yeah, I should move along here. Okay, so now we have a couple of different techniques. So we might want to think about comparing the Laplace mechanism to randomized response. So they both provide the epsilon differential privacy guarantee, but they are different, right, in a few different ways. So qualitatively, they're different in that the Laplace mechanism assumes all the data has been collected by some trusted party, right? So you have all the data there, and some trusted party is going to compute the true answer to a query, add noise to it, and give back the noisy answers. Randomized response, on the other hand, does not require the data to be collected, the data collector to be trusted, okay? So it's also known as a local algorithm because basically each record is perturbed locally and then sent on to some data collector who doesn't have to be trusted because that local perturbation has already created the privacy guarantee. In terms of utility, basically I'll skip over the details here, but the Laplace mechanism is much more accurate for a single query. Essentially, you can add random noise that's proportional to 1 over epsilon, whereas with randomized response, the error of the noise is roughly root n, okay, where n is the number of records in the database. So given just a single query, it's much better to collect all the data and just add noise after the fact than perturbing each record individually. Okay, so I walked through the definition of differential privacy and some basic algorithms. Now let me talk about some of the composition theorems. Okay, so Ashwin alluded to the importance of composition in the beginning of this tutorial. I'll say a few more things about compositions. So just informally, the idea of composition is thinking about running multiple differentially private algorithms, possibly in serial or in parallel. And it's valuable to have composition because it's very difficult to reason about the privacy risks of some complicated algorithm, right? So you want to do deep learning on your data. How do you think about the privacy risks of running a deep learning computation, right? It's not straightforward. On the other hand, if you can break down that task into smaller subroutines that access the data, and you can reason about the privacy risks of each of those subroutines, then you can use composition tools to basically figure out the overall privacy loss of running a series of those subroutines on your data. Okay, so the idea is it'll help with software design because we can take complicated algorithms, break them down into smaller building blocks, and reason about the privacy of those smaller building blocks. But of course, if you're thinking about the Laplace mechanism and thinking about adding noise to each query, you might say, well, if I just keep asking queries, right, I'll get back noisy answers. But at some point, you know, what if I just ask the same query over and over again, right? It seems like intuitively maybe that would leak too much information, right? Because for instance, I could just ask the same query over and over again and then average the results. Okay, so this is related to composition. So every time we ask a query, we are leaking some information about the private data. And this is the goal, right? This is the idea of statistical database privacy is we want to actually reveal aggregate information about the data. And so we are leaking information about the data intentionally. But as you might suspect, that's going to imply a limit on the number of queries that you can answer. Because if each one leaks some information, if you answer too many of them, you can actually potentially reconstruct the database. And in fact, there's been some seminal work on that exactly that database reconstruction problem. So there's a paper at PODS in 2003 that showed that you can actually reconstruct a database by asking roughly n log n squared queries, even if each query has noise that has random noise added to it that's up to root n error. Okay. And I won't go into the details of how this works, but this is a powerful result that suggests there might be some fundamental limits on how many questions you can ask if you only add a relatively small amount of noise to each one. Okay, so now we can think about the composition of differentially private algorithms. So here's the first and simplest form of composition. So if I have k algorithms, okay, and they all take as input this private database, and each one satisfies differential privacy, right? So we'll use epsilon I to indicate the differential privacy guarantee of the ith algorithm. If I run all k of these algorithms, basically those epsilons add up. So you can think of each epsilon as sort of the privacy risk incurred by running that particular algorithm. And if I run them all sequentially, the privacy risk accumulates in a linear fashion. Okay. So one way to think about this is it sets up an optimization problem. And so there are three axes to this optimization problem. So one is that you have privacy, right? You want to limit the privacy loss that is incurred by analyzing the data. You have error. You want to answer each query as accurately as possible. And then you have this kind of inherently a limit on the number of queries that can be answered, because each time you ask one, the sort of privacy loss accumulates. Okay, and so you can imagine you could impose some privacy budget. You want to say, I want the total epsilon of all of my interactions with the data to be at most some particular quantity. And then you can explore sort of how you can achieve minimum error within this space. Okay. And so we're going to look at actually some specific techniques that kind of explore this optimization problem. And so one really useful tool is to not just rely on sequential composition, which is the most basic composition, but look for more advanced ways that you can compose these algorithms. So one that I'll show you now, and later in the tutorial you'll see some more advanced composition results, is parallel composition. So the idea behind parallel composition is the following. So again, I have k algorithms, but this time I'm going to run them on k disjoint data sets, right? So I take my original data set, and let's say I partition it. So I partition by nationality, right? So I have a different data set for each possible nationality. If I run all k of these algorithms in parallel, right? So each one runs on a different subset of the data, then the overall differential privacy guarantee is actually the maximum of these k epsilons. Okay, so this means that the privacy loss is actually quite a bit lower than with the simple sequential composition. Okay, and then the final composition result is post-processing. So this says that if I have some algorithm and it's epsilon differentially private, okay, I can run it on a private database. And then I can do basically whatever I want with the output. So I can take some arbitrary algorithm M2, and that algorithm doesn't have to satisfy differential privacy. It's just going to operate on the output of M1, and it can do whatever it wants, right? And this is in contrast to, say, the k-anonymity, which Ashwin described in the beginning, where if you can actually take the output of k-anonymity and do some additional post-processing and get back private information. This basically says you can do whatever you want with the output, and you won't break the differential privacy guarantee. Okay. So I think in the interest of time, I'm going to skip this example of k-means clustering. But just to say that you can take the building blocks that we just talked about and take a statistical task like k-means clustering and basically use the Laplace mechanism and sequential composition to run a differentially private version of k-means and get back the centers of the clusters. Okay. But in summary for this module, so differentially private algorithms ensure an attacker can't infer the presence or absence of a single record in the input based on looking at the output of the differentially private algorithm. And we looked at some key building blocks, so the Laplace mechanism, the exponential mechanism, and randomized response. These will show up later on again. And then these composition rules help us build complex algorithms out of these simpler building blocks. Okay. So I want to move on to the next module, but I'll stop now and see if there are any questions about the basic definition of differential privacy or these composition results. Yeah.
Thanks. Very silly question, because is there any significance in behind the constant E, or just there for easy mathematical manipulation?
Of the epsilon or
Of the E,
oh, the
of the base,
exponentiation?
yeah.
No, yeah, there's no, you can use, it's just, no, you can use any constant.
Okay, thanks.
Other questions?
Yeah, if I can ask a couple questions. So how does it differ from when I'm using, you mentioned categorical data and say that I have like continuous data, adding Laplace noise to discrete data? How does that look like?
Yeah, so you wouldn't want to use the Laplace mechanism if the answer to the query is a categorical response. You wouldn't want to use the Laplace mechanism. You can use the exponential mechanism, and then basically what you're going to do is you sort of turn it into a numerical problem by saying, I'll assign a score to each possible categorical output, and then I'll define a probability distribution based on that score. That's the key idea behind the exponential mechanism.
And one more question. If I'm doing an aggregate, computing over those aggregates after those, say I have like some type of SQL statement and there's a group by, then a halving. The halving, it comes to no penalty. It shouldn't be it shouldn't be a differentially private algorithm.
If you said like, right, I want to compute sort of the number of people in each geographic area, and then the halving clause would be sort of, and I want the number to be at least 1,000, right? Give me back the zip codes that have at least 1,000 people with some condition, right? Yeah, what you could do in terms of the differentially private algorithm is you could first compute noisy counts, and then as a post-processing step, invoke the halving clause to sort of filter out results you don't care about.
Okay, and if I do a group by, actually, never mind.
So group by is an example of using parallel composition. You're basically breaking your data up into groups, and then you can use the parallel composition on each group. Yeah. Okay, good questions. There are some subtleties with group by, but I don't want to get into those right now. Maybe we can talk over the break. Okay, great. So I want to give you a quick tour through some of the techniques for answering queries on tabular data. So this is, I'll talk about some seminal results, some theoretical results on sort of what you can do in this space. And then I'll give a kind of overview in terms of algorithm design ideas with references to specific algorithms that you can check out. But I'm not going to kind of go into the details of specific algorithms. And I'll conclude with a few open questions. Okay, so here's the problem formulation. So we have a private database, D, consisting of just a single table, okay? And you can think of each tuple as representing the data of a single individual. And then I have a workload of counting queries, okay, that have arbitrary predicates. So select count from D where P, and P is some arbitrary predicate that could depend on any combination of attributes. And the output is going to be, the desired output is noisy answers to this workload of queries. And of course, the requirement is that the query answering algorithm satisfies differential privacy. You can extend counting queries to include linear queries, where basically you apply a user-defined function to each tuple, you map that tuple to some number between 0 and 1, and then you're just computing the sum over those. But for the rest of this module, you can just think about counting queries. So just to kind of motivate counting queries, you can actually do quite a lot with them. I mean, I guess as a database crowd, this shouldn't take too much convincing. Just to show you a few real-world examples. So spatial and temporal analysis, you can often basically break up your data by time and space and look at the number of records sort of within a time interval or within a geographic region. So here is a sort of the mood of the US according to tweets, right? So basically you can do some sentiment analysis on each tweet, decide whether it's happy or sad or not, and then count up how many tweets you have within each county and over time. Another example is the US Census. So they collect a lot of data about about people living in the US. And they publish a ton of statistics, which you can basically think of as a collection of counting queries. In particular, they publish a lot of marginals. So a marginal over a collection of attributes, say A1 through AK, reports the count for each combination of attribute values, okay? You can think of these as equivalent, it's synonymous with data cubes, contingency tables. So you probably can't see it's sort of a blurry image there, but you could imagine doing a two-way marginal over employment status and gender, right? And counting up how many people are employed and by gender as well, okay? And the US Census published thousands of these marginal queries every year on data that they collect. Another example is genome-wide association studies. So the goal here is to study genetic factors associated with a given disease. And basically what you do is you collect subsets of the population with the disease. So those are case and then without, so a control set. And then you extract SNPs, so specific DNA subsequences from these individuals. Typically, these SNPs have a few different alleles, so kind of variations on the gene that arise through mutation. And then what you want to do is sort of counting queries where basically you're computing the number of allele frequencies for both the case and the control groups, right? And the idea here is to find sort of DNA sequences that are strongly associated with the disease, right? And that suggests maybe a genetic cause behind the disease. And so you can compute these queries and then plug them into any kind of statistical analysis you want to do, like a chi-square test to find ones that are strongly associated. Okay, so those are three sort of examples of applications. Now we can unpack that problem a little bit of answering queries and look at a few different variants. So one variant is offline versus online, okay? So in the offline setting, you're given an entire workload as an input, and you get to compute all of the answers to those workload queries in batch, okay? In the online setting, you're given the workload arrives as a sequence of queries, okay? And they're potentially adaptive, right? So the analyst choice for query QI could depend on the queries that it asked previously and the answers that it got back, right? So this is sort of more of an interactive setting where the analyst is looking at the data and adaptively deciding what to do. And it turns out, and as you might suspect, that answering queries online is actually strictly harder than answering them offline. If you have all the queries ahead of you, you can design more accurate differentially private algorithms than you can if you don't get to see the queries until they arrive one at a time. We can also look at the problem in terms of some key aspects of it, okay? So I'll organize those in terms of data complexity and query complexity. So data complexity, you can think about the dimensionality of the data, so the number of attributes in the data, and then the domain size of those attributes, right? So you can think of the domain size of the entire data set as just the number of distinct attribute combinations that you can have. And a lot of the techniques that have been developed are specialized for low dimensional data, okay? So say a single dimension and a reasonably small domain size, or maybe two-dimensional like spatial data. We can also think about query complexity. And so a lot of techniques are designed to work for a specific class of queries. So I described counting queries as a specific class. But we can even think of kind of subclasses and superclasses of counting queries. So a histogram is a specific form of a counting query. You can imagine range queries over some kind of ordered space. Marginals I described before, counting queries, and then linear queries are a kind of generalization of counting queries. And they're sort of ordered here in rough order of difficulty. It's easier to design differentially private algorithms for histograms than it is for arbitrary sets of linear queries. And then in terms of, so those are aspects of the problem definition. In terms of the solution approach, there's kind of two key solution approaches. So one is a kind of direct approach where you're basically given this workload of queries and you basically output answers to every query in that workload, okay? Another approach is the synthetic data approach, where basically what you do is the differentially private algorithm will construct what's called a synthetic data set, D prime, which then it gets published, okay? So this is sort of, I say it's synthetic data set. It may be based on the real data, but it's based on differentially private computations on that real data. And so it really contains a collection of sort of fake records that are a close proximity to the original data. And once that data has been published, an analyst can do whatever they want with it. So they can ask any query they want. Of course, the answers aren't always going to be accurate, right? So some queries that they ask on the synthetic data set may have high error. Okay. So let's talk about two theoretical results. So first, given that the negative result of Denur-Neeson that said, right, you can only answer, if you add square root of n noise to each query, you can only answer so many queries before you can actually reconstruct the database. So you might say, well, how in the world can we answer a workload of queries given that negative result? So there's a way of kind of getting around that negative result. And the key is to recognize that the Denur-Neeson result was under the model where the query answers had independent noise, right? And the intuition is if you're adding independent noise to each query answer, well, then that noise can cancel out in various ways, okay? And that's sort of the key to their attack. If we want to get around that, we need to think about structuring the noise so that the error in each query is somehow correlated, okay? And we'll see some examples of correlation throughout the tutorial. So, and I'll just sort of give you two high-level ways that query answers can be correlated. So one is that we could use some query answers that we've already released to approximate the answers to other queries in the workload. And I'll show you a concrete example in just a minute. But intuitively, if I've sort of already answered a very similar query, maybe I can just approximate the answer to a new query based on the queries I've already answered. Another way you can kind of generate correlated noise is by the synthetic database construction, right? So I'll construct a single database that's approximately accurate for all the queries of interest. Of course, the errors in those queries might be correlated because they're all based on this one synthetic data set. So there's a positive theoretical result that says you can actually answer exponentially many queries in an offline setting, okay? And maybe I'll skip over the details of this, but I'll just mention the sort of key technical insight is that basically for any set of queries that you want to ask about, W, counting queries, there exists a small database D prime that's consistent with your original database for every query in this workload, okay? And by small, I mean that the size of that sort of synthetic database is logarithmic in the number of queries that you want to ask. And then alpha here is your sort of error tolerance. So by consistent, I mean that the error for any query in the workload is at most this alpha term. Okay. And this result follows from learning theory, right? So what learning theory tells you is that if I do machine learning on a small sample of data, right, it'll generalize to out of sample results, right? And so the basic idea that they're leveraging here is that notion that I can construct a small sample and that'll be a good proxy for the larger data set. Okay, but so the way they actually, the key to their technique, that's sort of the key technical insight. How their technique actually works is as follows. So given the workload and epsilon, they're going to output a synthetic data set D prime. And what the mechanism does is it constructs T, the set of all small databases, okay? So it like literally enumerates every single possible small database. Then it uses the exponential mechanism. So it basically says, the degree to which I like a particular small database is how close its answers, the query answers are on that small database as compared to the true database, okay? And then I will sample a small database using the exponential mechanism that I described before. And what the theoretical analysis shows is that with high probability, the error is going to be at most bounded by the log of the domain size, the log of the size of the workload over epsilon and the size of the database. Okay, so if you kind of rearrange things here, you can actually answer exponentially many queries with constant error. Okay. So this isn't really, the focus of this tutorial is differential privacy in the wild. This is not a practical algorithm because it requires actually enumerating all possible databases. So it has runtime that's exponential. And so, we'll look at more practical techniques in a second. But another result, if you're interested, is, another limitation of this is that it's offline only. So if you're interested in the online setting where queries are arriving over time, there's another result by Hart and Rothblum that develops a technique that allows you to answer exponentially many online queries. But I won't go over the details of that. Okay. So what I'd like to do to kind of to talk about some of the practical techniques that have been developed is take a particular case study. So let's look at range queries over spatial data. So let's say we have a data set of like taxi pickup and drop-offs in, say, Beijing, right? And I want to answer, so my records here are particular pickup and drop-off events. And what I want to do is be able to answer range queries on this data, right? So I might want to know, I might have a workload of say 3 range queries. I'll consider larger workloads. And I want to know how many pickups or drop-offs occurred within this particular range. And this could be useful for city planning and things like that. Okay. So we can start by thinking about a really simple baseline algorithm. Okay. And we'll see it has some limitations, and we'll look at some ways in which we can improve it, and I'll kind of give you pointers to the research results that have improved algorithms out there. So the first thing we might do is we have this spatial data. We can discretize the attribute domain into cells. Okay, so we'll form some discretization. Then we can use the Laplace mechanism. We can count up the number of, say, taxi pickups in each cell, and then use the Laplace mechanism to add noise to those counts. Okay. And then we can use those noisy counts to answer queries directly, right? And so what we might do is, right, if I get a range query like this that overlaps partially with some of the cells, I could assume a uniform distribution within the cell, right? So if the range query only covers half the cell, I'll take the count and divide it by 2 and include that in my answer. Alternatively, I could generate synthetic data, right? So I have this kind of collection of noisy counts over this grid, and I could derive some distribution from those counts and then draw samples from it. And then I could release that synthetic data and people could query that synthetic data. Okay, so this approach has a couple of limitations. So one is the granularity of this discretization, right? If I make it really coarse, then I lose detail, okay, right? I'm gonna cut up the city into only, say, a small number of quadrants. I lose the fine-grained detail of what happens downtown. On the other hand, if I make it really fine, then the noise that I add for privacy protection is gonna overwhelm the signal, okay? And in fact, what happens is the noise accumulates, right? So if I'm answering a long-range query, the amount of noise, since there's noise in every single cell, if a range query requires summing many different noisy counts, right, that noise will accumulate. And I can show you that pictorially, and I'll come back to sort of an alternative algorithm and compare it side by side with this. Just to explain this figure, so this is just one-dimensional data, so we're no longer spatial data, but just some, say, histogram over 128 possible values, okay? And then what we can think about is employing that baseline algorithm on this data. And then I want to answer all possible range queries, right? So that upper left corner there is just the range query that just looks at the first cell. So how many records are in the first cell? The lower right there is how many records are in the last cell. And the lower left here is the total number of records in the entire data set, okay? And what this shows is that the baseline algorithm, it has fairly accurate answers for the individual counts, right? Because you're just adding a small amount of Laplace noise to each one. But if you ask long-range queries, the error accumulates, right? And so you get this bright yellow indicating high error for large ranges. Okay, so let's come back and look at how we can do better. Okay, so an improved algorithm is the private quad tree. And there's been many techniques. I'm just using this one as an illustrative example. And the basic idea is that you build a quad tree over the data. And so you'll recurse on the nodes of the tree, right? So you start with some root node. You add Laplace noise to the count, so the total number of records in the data set. Then you split that root node into quadrants, right? So into 4 children. You create child nodes underneath that node, and then you recurse, right? And you keep doing this process on each child node. And you'll stop when the noisy count gets too small, right? So less than some threshold L, or when some maximum height is reached. And so the intuition behind this algorithm is, one, the early stopping is going to control the granularity of the discretization. So I'm only going to drill down into the data where there's a large count. If the count gets small, I'll stop drilling down, and I can summarize the data at that point. And then the other thing is this helps with range queries, because to answer long range queries, I can rely on some of those noisy counts that are higher up in the tree. Okay. So exactly, I'm going to skip over this. So exactly how does that work? So how can I answer range queries using this quad tree structure? Right, well, each node in the quad tree has a noisy count. So one idea, the kind of simplest approach is as follows. So given a range query, I could just find the smallest set of noisy counts from the tree that cover that range query and sum them up, okay? But there's a better idea, okay? So the idea, and it's based on an observation. So the observation is that a node's noisy count and then the sum of the children's noisy counts are both, Sorry, I'm getting an error message here. They're both estimates of the same quantity, right? The count at that node, okay? And so the idea is we could take all of these different counts and combine them, and we can get a single estimate using statistical inference. Okay, and I'll come back to that point in a second. But the result is something like this. So with the quad tree algorithm, you end up getting much more accurate results for larger range queries, right? So you can see the error for some of the large range queries is lower. You do end up incurring slightly higher noise for some of the smaller ranges. So there are some trade-offs, but for large domains, this can be much more accurate for answering range queries. The error is more polylogarithmic rather than linear in the size of the range. Okay, but this tree example is really just an example of a more general pattern of doing a data transformation. So the basic idea, and so there's a lot of different techniques that follow this basic pattern. The basic idea is you have your original data, you transform it in some way and get a collection of coefficients. So with the tree, those are the noisy count, the counts in the quad tree structure. We can add noise to those for privacy. Okay, now we have a set of noisy coefficients. It's safe to release those. We've satisfied differential privacy. But we can also take those coefficients and kind of invert them using statistical inference and get back some private data set. Okay. And the goal here is, the tree is just one example of a data transformation, but there's lots of different transformations we can consider. And the goal is to pick a low sensitivity transformation that preserves good properties of the data. So the tree is explicitly designed to support long range queries accurately, right? But depending on your workload, you might want to emphasize other aspects. And so in fact, there's been a large number of different data transformations that have been proposed. Almost all of them are linear transformations of the original domain of the data. Various tree structures, wavelets, Fourier transforms. And with all these, you can invert the transformation. And some of them actually have redundancy built into them. So the quad tree has some redundancy. And so rather than just computing a straight inverse, you do a pseudo inverse. The matrix mechanism was work that kind of formalized this general pattern of employing a linear transformation and formalized the problem of designing the best linear transform for a particular task. Okay. One property of all these different techniques is that the error rates are independent of the input that you're running on. Basically, all of them, if you analyze the error, it has a closed form solution that just depends on the Laplace noise that you're adding in, and it doesn't actually depend on the data. So an alternative is not just to think about linear transforms that are directly invertible, but to actually think about lossy transformations, okay? And here's where there's been quite a variety of different techniques. So some kind of simple ideas is do a linear transformation, but then drop small coefficients. So we saw that with the quad tree. If the noisy count was small, we just simply stopped recursing down the tree. There's data adaptive discretization. So instead of building a histogram with a fixed structure, you could have the histogram bin widths designed adaptively based on the data. You have to do this carefully to ensure that you satisfy differential privacy. And then there have been other techniques, including randomized transformations and things like sketching and smoothing, and compressed sensing. With these techniques, though, because the transformation is lossy, now the error rates depend on the input, right? So if you're working, say, with sparse data, and you drop some of the low coefficients, then you might still be able to reconstruct an accurate result. On the other hand, right, you're sort of choosing to throw out some information, and so you're implicitly injecting some bias into the calculations. And so on the one hand, that can be good. You can trade off a small amount of bias for dramatically lowering the variance. But to evaluate these techniques, their error rates actually become data dependent, right? So it becomes much trickier to evaluate them and figure out whether it's offering a good privacy utility trade-off. Let's see. Maybe in the interest of time, I'll skip over. I'll just mention there's some work on higher dimensional data. So this was all focused on low dimensional data. So there's been work on taking things like Bayes-net structures and adapting them to make them differentially private. And then there's also been some work on benchmarking these techniques, right? So a ton of different techniques have been developed. As I mentioned, some of them are data independent, so the error rates don't depend on the data, and you can simply look at a closed form solution for their error. On the other hand, some of them are data dependent, which makes empirical evaluation really important, right? You want to know, when will this algorithm work well? Is it only going to work well on some data sets but not others, right? And what are the characteristics of those data sets that's going to make this technique work well? And so some of this was at a paper that appeared at SIGMOD last year, a fairly exhaustive study of all the different algorithms that have been developed for 1D and 2D histograms. And one of the findings was that some of the data-dependent techniques that I described, they don't offer benefits at larger scale. So scale being the number of records in the database. So basically, these techniques work really well when you have small data sets or very sparse data sets. But as the data set gets bigger, some of those data-independent techniques end up having better performance. Okay. So just to wrap up with a couple of open questions. So given that there's this wide variety of data-dependent techniques out there, an open question is how to select the best algorithm for a particular task, okay? And I'll just give you a forward pointer to a paper that's at SIGMOD on Thursday in the differential privacy session. And it introduces Pythia, which is a technique for actually selecting the best algorithm from among a set in a differentially private way. Coming up with error bounds for those data-dependent algorithms. So really trying to actually characterize, in the worst case, what kind of performance can I expect out of them, or even sort of error bounds that depend on properties of the data that potentially you could measure and evaluate. And then doing more in-depth empirical evaluation for some of the algorithms designed for high-dimensional data. Okay, so I will stop there. I can see if there are any questions.
One clarification, basically, when you had this quad tree, so, and if I give a range query, you find the node, that's the lowest node that covers the query, and you are combining it with its children, right? So what happens if, let's say, only 2 of the children covers the range? So you only use the 2 nodes for that statistical estimate, or all 4 of them?
Well, so the simple strategy would be to just, to just basically find a cover, so find all the counts that you need, and then wherever you can sort of get away with using a parent count rather than the children, then use the parent count, because that'll have less error. But with the statistical inference, you can actually formulate this as a least squares problem, where basically the unknowns are the true counts of the finest granularity cells. And then what you have is linear combinations of those unknowns with noise added to them. And so you can do solve a least squares inference problem and basically recover an estimate for each of the individual bins based on the noisy count.
Right. So basically, let's say the node, let's say there's n that covers the query, and this n will have 4 children, right? And let's say only 2 of those children are jointly sufficient to cover this query. So you only use in your least square equation, you only use those 2 nodes, or all 4 of them?
So with idea 1, you would, with idea 1, you would just use the 2.
Okay.
With idea 2, you can do inference to come up with an estimate for all of the sort of finest granularity counts. So all of those smallest granularity counts. And then that's fixed. And then when you want to answer a range query, you just sum up the estimates that you have for the individual counts. So it's sort of a 2-step process, right? So you first come up with an estimate. Once you have the estimate, you can sort of throw away the noisy counts you have and just sum up the estimates. Question back there.
Hi, I have a question about the parallel
Parallel composition.
composition. Yeah. So in the example about just can you go back to the map of the grid of cells?
Grid. Sure.
So it seems that, say, if you have a counting queue, I mean, you output the count of each grid once for a grid of n times n. It's by parallel composition. It seems that the privacy is consumed by epsilon.
Yes, exactly.
But if you say you answer n times n counting queries with different predicate, does that actually consume n times epsilon privacy for this data set?
Let's see.
So for example, a predicate might be x-axis is from 0.5 to 0.6 and the y-axis is from 0.5 to 0.6, and you iterate over this data set with different cell, and you answer this counting query over this entire data set, but with different predicate.
Right. Yeah.
And
So,
for each
okay.
one, you apply different, you apply the Laplacian mechanism.
Yes.
So does that actually accumulate the privacy, or actually the n times n counting query still consumes the?
Okay, so I think I understand your question. So if you ask predicate queries that overlap, then what you're left with is the sequential composition. So the privacy loss accumulates. So like if I ask this query and this query, they overlap, right? And so I can't use parallel composition. But the idea behind this algorithm is that I'm gonna break the data into this grid of disjoint regions. Then I can ask noisy counts for each disjoint region and exploit parallel composition here. And then if I want to answer a range query, I can just take those noisy counts and sum them up. And so in that sense, I'm sort of getting around the sequential composition by I'm doing the parallel composition to get the noisy counts, and then I can sum them up however I want. And I don't have to worry about the situation that you're describing where the privacy risk accumulates. Question? Yeah.
So we have to know. So it sounds like we have to know ahead of time to like separate them into cells. So at any point, I can't choose to go back to the other method. And if I were to choose at that point, like to go from doing parallel composition to sequential, do I take like the worst affected cell and start from there and sequentially add to that cell, or would I just not be able to?
So these compositional results, you're free to sort of mix and match, right? So in fact, one way to think about the quad tree is that I'm interleaving sequential and parallel composition, right? So there was a quiz question in there about the privacy risk of the quad tree that I skipped over. But each time I'm dividing into quadrants, I'm leveraging parallel composition. But then I'm descending down this tree. And so that if you look at the levels of the tree, the composition that I'm using there is sequential composition, right? So you're free to, say, build one of these trees, and then if you have some of your privacy budget left over, right, you could ask additional queries in areas where you thought you wanted to improve the accuracy.
Okay, so if there's, I asked two queries that have two sets that like overlap some, do I have to, and so I can't use parallel composition. I have to use sequential composition, like here.
So something like this, yeah.
Yeah.
Well, so here, what you could, like a strategy would be, oh, I want to answer those two queries, they overlap. Let me break them up into a bunch of different queries, right? So I could basically take the overlap, ask that, and then ask for the disjoint parts. Then I'd have parallel composition, and then I can just sum up the parts that I need to answer the original queries of interest.
Okay.
Yeah. Okay, well, I should let you guys get to the break, but I'll just say that in the second half of the tutorial, we'll go over some of the really cool state-of-the-art techniques for machine learning, looking at trajectories, as well as social network analysis. So I encourage you to come back to the second half. Thanks.